So, hello everyone. My name is Ivan. I work at Tinkoff as a data scientist in chatbot development team. And today we're gonna cover some interesting topics regarding paraphrase identification, paraphrase retrieval, how to use attention mechanisms solving this task, and probably that's it. If you'd like to follow the lecture, you can go to this link, then download Jupyter Notebook and just follow the lecture. Okay, but first, what is paraphrase identification task? Imagine you have two texts and you need to predict whether these two texts have the same meaning. If they have the same meaning, it means that those two texts are paraphrase. On the other hand, if texts have different meanings, that it means that they are not paraphrase. In this tutorial, we're gonna use for question pairs dataset, which is basically dataset about paraphrase identification task, and it consists of 3 columns. First column is text, the second is text, and the third is labels. If you see label equals to 1, then it means that those two texts are paraphrase. So what are good scary movies and what are some best scary movies probably have the same meaning. On the other hand, if you see the label equal to 0, then those two sentences are not paraphrase. So can a poor person get a good job, and how do I found a good job? Those sentences have absolutely different meaning. We start our tutorial by dividing our data set into 3 splits: train, def, test, and we will think about baseline approaches as how to solve this task. The first thing that comes to my mind is to somehow represent text into a numeric format and then calculate some measure of distance between those vectors. So, first, how to represent text in numeric format. The obvious approach is to use bag-of-words algorithm, which just counts how many times a word appears in a document, and then it represents a text by a vector of size of which equal to a vocabulary size. Okay, and then imagine we have 2 texts, T1 and T2. Then, using bag-of-words, we transform them to x1, x2, and then by some similarity measure, here we use sign similarity, we're gonna compare these vectors. So we like to calculate some distance between those vectors, and if this distance is above a certain threshold, then we say that x1 and x2 are not paraphrases. And if the situation is otherwise, if distance is below the certain threshold, then we say that those texts are paraphrases. Okay, let's do this. Let's transform our data into numeric formats using bag-of-words algorithm. And as you can see, let me check my internet connection. Okay. something's wrong. Let me restart the kernel because I don't see what's wrong. Okay, let me first kill something. So we represented our data set in using bag of words, and as you can see, we have in trend set we have 20K features and 20K samples, which is not good because if you have 20K features, then any algorithm will work pretty slow. And as you remember how we decide whether two sentences are paraphrased or not, we calculate distance, and then on the def set we find the optimal threshold. Like we just iterate over some space of thresholds. Here you see that cosine distance is bounded by 0 and 2. So we just find the optimal threshold on the development set, and that's 0.65. So if the distance is above this threshold, then we say that sentences are not paraphrases. And then we like to calculate the metric, which is F score in our case, and you see that on the test set we have this kind of value. So let's create a table in which we're gonna put those values and compare them later. So bag of words approach on the test set gives us this value. Then how to improve this approach? Pretty simple, just use TF-IDF representation. TF-IDF representation is just a simple algorithm that instead of just counting words, it uses coefficients between, it uses the following method. If the word occurs very often among documents, then we lower its coefficient, and if the word is rare and it occurs many times in a text, then we increase the coefficient. So using the same procedure, we transform our initial data into a numeric format. Again, it's a 20K by 20K table. Then we calculate scores and see that TF-IDF slightly improves the initial score. Okay. And now it's something like this. But as you understand, if we work with complex languages such as Russian, there are many situations when we have a slightly modified word. For example, if we have word cat and cats, then by comparing vectors using bag of words or TF-IDF, we'll see that distance between those two vectors will be like maximum. And it's no good because, especially in Russian language, there are many endings that change a word a little, but the meaning probably won't be changed. So how to handle such problem? Probably what we need to do is to build TF-IDF representation not on top of words, but on top of characters. And how to do that? We can pass these arguments into TF-IDF vectorizer from sklearn, pass values 3, 5, which means that if we have words like hello, then we're going to transform it to and so on. And for this is 3 grams, 4 grams, and 5 grams. Yes.
Why not to try to normalize the text? For example, to remove this non-informative parts of the
Stop words.
yes. To remove the endings of the
You suggest to, for example, lematize the word. Yes. Yes, it's also possible, but this approach is also useful when you have, for example, if you don't know how to write this word and you just do like this, then using character engrams, you still capture some word information. And if you, no, so, okay. But in this case, as you can see, dimension of the initial data set will be really big. It will be, okay, wait for a second. Now it's 170K features versus 20K samples, which is very bad, but still we can calculate our metrics and see that still it's English language, still it improves our score on characters a little bit. But if we use Russian, then I can guarantee you that it will be like a very good improvement compared to naive TF-IDF. But I'd like to ask you a question. Why bag of words and TF-IDF probably may fail on this task of identifying whether these sentences have the same or different meaning? Any guesses?
They don't reveal long-term relation between words and meanings.
Okay, what else? Okay, what else? Imagine we have
Perhaps they I may use some dynamic words to ask the same question.
yes, exactly. The main problem is when we have two texts, then we can express the same meaning using absolutely different words. And the same for not paraphrases. We can express different meanings with the same words. So we need to somehow mitigate this issue and develop something more powerful. And the first thing that comes to my mind is to use some unsupervised methods that represent words in a dense format. So this is how. A word-to-vehicle fast text is an unsupervised method. We can simply train a model that can transform our data into numeric formats with a much lower size. And how to represent a text in numeric format. What we'll do is we're going to transform our initial text into tokens, then tokens into word vectors using fast text, for example. And then we're gonna average them to receive the representation of text. And then, using the same algorithm as before, we're gonna find the optimal threshold and calculate scores on the test and def sets. So that's what we do. Now we see that it's 20K features versus 300 dimension. On the development set, we get we get 56, and on the test set, 57. Why do you think this algorithm failed? Overfits? Okay. How about underfits? Because we have only 20K examples, and it's probably not enough for the algorithm to converge and to give some embeddings with useful information. So what we can do is to download models, pre-trained models, which were pre-trained on large corpora, for example, on Wikipedia. I won't do this here because it's a little bit slow, but as you can see, it's the same thing, and it scores on the test set pre-trained. Okay, but still, it's not a good score. We need to improve it. Any guesses why fast text is not a good algorithm for this task? So it's the same as before. We use fast text to convert text into embeddings, but as you can see, scores are not good enough.
How fast text accumulates representation for different words?
By averaging.
That's a problem.
Okay.
Average, unaverageable.
Average and averageable. What do you mean by unaverageable?
I mean, we average different meanings, and output is something between these words, but it can make no sense actually.
Yes, this is the right answer, because when we receive vector using fast text algorithm, we think that inside this vector we have a perfect information about the initial texts, like this is elements of the vector. Okay, this is xi, and the same for xj. Then what we do, we calculate site similarity. Actually, this is just element-wise multiplication, normalizing, and summing. It's no good because we have no guarantee that just by multiplying two vectors will solve our problem. Because who says that if multiplying these two values gives us high value, then this should be a paraphrase? No. So the answer is fast text just gives us not a useful vector, not efficient vector. Okay, But how to improve this algorithm? One idea is to build some, yes?
One more question. In practical applications, wouldn't the first thing to try would be to obtain somehow more representative text corpus? For example, to train this embedding on the more large
Fast text?
data set, yes, and then use it on retrieval.
Yes, that's exactly what we did. Here, fast text pre-trained is a model that was pre-trained on a large corpus, Wikipedia. Yes, and as you see, it's better than fast text that we trained from scratch. So, as I was saying, just by multiplying two vectors, we won't receive useful information. What we need to do is to somehow calculate interactions between vectors, for example. So we need to create a model that decides on which elements, let's assume this is a model. Model decides on which elements of the vectors to see to understand whether these two vectors have label, for example, label, predicted label. Okay, how to do that? The simple idea is to just concatenate these vectors and pass it through dense layer. That will predict the label. Okay, and first, what we need to do is let's save our data splits. Then we'll have this object that generates iterators over the data sets, and it returns these iterators. And as you see, wow. Sorry. We can actually do it on CPU for a while. So, what's inside the batch? As you remember, query question data set consists of 3 columns. Text 1, text 2, and labels. Batch size equals to 64. And we can look at our data. Each batch is just a matrix. Here you can see, for example, for the first text, it consists of some indices, and each index refers to one word. So we can actually see to which word refers each index. For example, 57 refers to V, 151 refers to lows, and so on. We can just check what's going on. And as you may imagine, in each batch there are different texts of different lengths. So if the text is small, then we padded them by a padding token. In our case, it's 1. So as you can see, this is just initial text, then we pad, and so on. So as I said, our model will look like this. First, it transforms our initial text into embeddings using embedding matrix. And how to do that is to initialize some random matrix with the size of vocabulary size. Let's say this is embedding matrix. We choose some embedding size, which is in our case equals to 64, for example. And here we put number of tokens in our vocabulary. So for each column, we have a word here. For example, here we see hello. Here we see animal, for example. Okay, then there is a body. This is any architecture you like. It can be LSTM, transformer, some CNN models, and other guys. So this is anything. Then this body outputs text representation for the initial texts. And then we have head, which decides and which outputs probabilities for two texts, whether these two texts are paraphrases or not. So okay, let's code it. It will be pretty simple. First, as I said, we have embedding layer. Of size number of tokens and embedding dimension. This is how it looks. We can, as you remember, we have batch where we can find text1 and text2 of sizes, batch size by number of tokens in the batch. Then this object embedder can transform tokens, indexes of tokens into embeddings. So as you see, firstly we had 22 tokens for each sample in the batch. Then we can, what we did is we transformed each token into a vector. So that's why we have another dimension here. Okay, then, as I said, we have a body, which just given some embeddings, it outputs vector that represents text. Okay, and how the simplest way to represent the text, as we did before, we just average embeddings. Then we pass this aggregated vector through some fully connected layers. In our case, what we did is averaging network, which does the following. It receives embeddings, then it aggregates it by min pooling operation of tokens. Then we have linear layer that transforms it into another dimension. Then we have relu activation and another dense layer. Okay, so what we had before is embeddings. Then using body we just coded, we transformed our embeddings into another dimension. So now, for each text in a batch, we have a representation of these texts. This is a very simple approach, but anyway, we stay with it. And then head, which classifies whether two sentences are paraphrase or not. As I said, just the basic approach would be to concatenate two vectors together. Let's say we have x and y. We concatenate those vectors, and then we just create a classifier that looks looks on each vector and transforms it into probabilities. Why it's better than just sign similarity? Because this layer can look on each element of two vectors simultaneously. Why this is good? Because it can understand on what elements to look and decide what's important in specifically this task, paraphrase identification. Okay, so this is, we call it simple head. It receives two vectors, then it concatenates them, and then passes through one dense layer. In our case, dense layer is just this. So yes, now for each text, for each two texts, for each pair in a batch, we have, we can call it probability that these two texts are paraphrased. Okay, then let's put it all together. Let me remind you what we had. Our pipeline looks like this. First, it's always a text. Then, using embedder, we receive embeddings. Okay. Then, using some body layer, which can be anything you want, for example, LSTM. Okay. We receive text representations. And then we pass these text representations to the head, which decides, which solves our problem. This object was made to use these three other objects to put them together. So the final model looks like this. We have 2K vocabulary size by 64 embedding size. Then there is an averaging network, which from an initial size of 64, it converts vectors to the size of 16. And finally, simple head, just dense layer. Okay. So this is just a one-line example of how to convert texts into probabilities and into hidden representations. Pretty simple. Okay. Now let's try to train this model. We have some functions here that train our model for one epoch, validate, and do it together. We'll use binary cross entropy loss for our task, and this cell starts the process. But first, let me change device to GPU. Actually, we don't use the full data set because it will be pretty slow, and we'd like to receive results immediately. So let me first check, do we have some free GPUs here? Okay, how to, pretty simple. And that was me. Okay. It will be fast because we don't need to do the same operation again. This is our pipeline, embedder, body, and the head. And we can start the training process. I remind you, this just a simple approach that concatenates two vectors together and let the model decide what's important. These values represent the metric on the test set, so we can look just here. For each model, we'll just do 5 epochs, because after 5 epochs, model overfits, as you see here. On the train, it's already high values compared to the test set. And as before, we're going to put the score in our table. So we'll call it simple head model, which aggregates embeddings and several dense layers. As you see, it's a good improvement compared to other models. It's all because what we did is we concatenated two vectors together and let the model decide what's important. But how to improve even this pretty simple approach? I remind you what we need to have is interactions between these two vectors. Okay? The first thing we did is we concatenated them. What else can we do? What features we can create from those two vectors? Yes, multiplications. What else? Average. Okay. What else? Just, yes, difference. Just imagine you are in machine learning class and you need to somehow do a feature engineering and create something new that.
Perhaps we should somehow choose the optimal features for the Paraphrase.
Optimal features from these vectors. For example, this is a 16-dimensional. And how do we do that? Yes, but just what I'd like to ask you now is, imagine we already have a model which outputs text representations. And we have two vectors already. Mm-hmm. Yes. So all these ideas are good, but what we'll try to do very simple. Every algorithm here is just a baseline. It's in its own field. multiplication is, element-wise multiplication is great because it's, I remind you, firstly we try to use cosine similarity to understand whether two vectors are close to each other. But this measure of distance doesn't mean that if the vectors are close to each other, then there are paraphrases. We'd like to understand what features from vectors are important. So that's why, for example, element-wise multiplication creates new features that, let's say, we have some words here, and interactions between those two words give extra information. The same for difference, because if vectors close, then this thing probably will be elements of this vector will be low. Okay. So yes, very simple approach. We used to concatenate just two vectors. Now we create two new features and concatenate them with our initial vectors. So let's code it. We'll call it, so yeah, this is how it looks. Just element-wise multiplication, difference, and initial vectors. We'll call it sneaky head because it's sneaky. Here you can see element-wise multiplication, difference, and concatenation. And the final thing is a dense layer, which decides what's important. Maybe element-wise multiplication, maybe initial vectors. We don't know. We'll let the model decide. So, okay, once again, this is how model looks. In this case, you can see everything but head is different, is the same, I'm sorry. Embedding layer, averaging network, but now you see that head receives this number of features and used to it received only this. So, okay, let's train this network and see what it can offer. All right. We call it sneaky head. And look what it can show us. Okay, you see, using just a few lines of code with the idea that we need to look at interactions of vectors, we can still improve our score. We say that it's because for now, this is the best model, which will be hard to beat because it's a very simple but effective approach. But here we'll talk about attention and how it can help us to solve the problem. But first, we need to talk a little about attention, what it's all about. This image can help us to understand how to look here. Imagine we have two texts, one on the left and one on the right. Okay, here texts are similar, just word by word, but imagine we're solving paraphrase identification task, and here is one text and here is another. But still we can look at some insights here. What attention does, it's helps you to understand for each token on which tokens we should pay attention to. Here you can see example, the animal didn't blah 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 eat. It, it's another word for the animal because it's in a context, okay? And you see that this is those lines show how much attention should we pay to words from another text. Here, the animal gets the highest attention. This is not always true, but we'd like to train a model that will do the following. Will pay attention to words that matters the most, okay? And how to do that. But let me first ask you the intuition. We have two vectors, okay? Let me put them closer. Vector 1, vector 2. We said that cosine similarity is not good because it just looks at paired elements, right? So how to make the something to look not only these elements but look on other elements to receive a scalar? By mask. What mask? Zero and ones. Okay, let's say we have mask which zeroes out some elements here, and still it's no. Okay, yeah, if we transpose the vector, the initial vector, then it's a scalar because d by 1 by d, I'm sorry, 1 by d, d by d, d by 1. Yes, but how you would construct such matrix? By hands, right? By training. But you said it's a sparse matrix with the zeros and ones. Manhattan. Where should I put Manhattan? Yes.
Это нормированная метрика, когда считаются небеса, а когда считаются кварталы. То есть единица это переход между элементами, если они разные, единицы.
Okay. Manhattan distance, right? Да.
Тогда не надо нормировать вещи, для того, чтобы избежать как раз Retrieval, которая чувствительна к выбросам. У нас есть некоторая сетка, ну, если так пояснить, и необходимо в этой сетке как-нибудь дойти. Если бы было Retrieval, мы бы расстояние меряли, а здесь мы раз, два, три, 4. Расстояние 4. Вот эти все квадратики одной величины. Тогда нам нет необходимости избегать нормировки, которую вы раньше показывали, когда косинус считали, потому что вы там, если в этом косинусе еще вычесть среднее значение у этих элементов, тогда косинус работает. А если математическое ожидание не считать x и y, тогда можно попасть в неприятности.
Okay. But as I remember, this is exactly a Manhattan distance, right? Thank you. Okay, of course, we can calculate some L norm measure between two vectors, but still, it's just it compares pairs of each element of vectors, right? So we need to somehow improve this matrix. By hands, by what again? By optimization. By what optimization? What we need to optimize? Okay, good enough. Yes, what we can do is just initialize this matrix randomly with some any distribution you like. Not any, but you can do it anyway. The intuition. Here, let's put it this way. X, let's say it's W, and Y. What we used to do is we just, I remind you, just compare it to elements of vectors. Now, this matrix can decide what's important for paraphrase identification, because it's a trainable matrix, and we could put it anywhere. Because probably this matrix can decide that pairs are not important at all. Or it can decide that nothing is important. Or you can decide that last element is more important with the first element. So this is the intuition. This matrix transforms the cosine similarity into something learnable. Okay? But what we have two texts, and therefore many vectors. We have x, and y. X1 is the first embedding of this text. This is the nth embedding of this text, and the same for y. For example, it's I love pizza, and this is I'm a big fan of pizza. Okay. Here m equals to 3. Here k equals to 8. And we'd like to do this. For each word in the first text, we'd like to create a tension vector, which will tell us how each token from another text is important. Okay? So let's do this. We already said that we can use this learnable, trainable matrix to do this. So we say we have score S, which do the following. It calculates the score between two vectors. So the more is more, then this more important. Okay. Then we do this for each j. So we fix xy, then we iterate over all elements from the from the second text. Therefore, we obtain attention score by normalizing it using softmax. How to do that? Ij is this, Syj, and then we iterate over all scores here. Pretty simple. Therefore, yes?
Xi and Yj is vectors?
Yes, this is word embeddings. For example, you can think that these vectors are obtained from LSTM or even from embedding layer. So again, we receive for each x, we receive a vector because it's for many cases. How many cases? 8. So then it's we can construct attention matrix, which is m by k, and in our case, m by k is 3 by 8. And what we need to do, we need to train this thing. How to do that? We just put it into our neural network and it will decide what to do with it. But as you may imagine, this is just the simplest way to understand on which elements we should pay attention. Other approaches are like, let's see at minus attention. The intuition will be similar. Instead of putting this matrix here, and the task is still to output scalar, okay? You'd like something more smart. We can create a vector and a matrix and some nonlinear activation to receive these scores. One way is to use minus attention with the same intuition, x minus y. Okay, so now we first calculate the difference between two vectors. Then we let the matrix decide what elements of this vector are important. Okay. If we don't like to forget the dimensions, let's say what's here. Then it's just a vector. Okay. We apply this non-linearity, and then we have some context vector that decides what's important here finally, and still it's just a number. Okay, something. And using the same normalization algorithm, we just apply softmax and receive. Yes?
Why do we need actually softmax here? Because you can use, for example, two words as Retrieval. That's the words which requires attention or not.
Why do we need softmax, right? Because what we like to do is to aggregate information from another text. Let me clarify what I mean. And let's consider this case, okay? imagine that this token shows you different coefficients for each token from another text, right? Then let's say that only one token here has 1 and others are 0. Okay, like animal is 1, others are 0. Then we aggregate the text from there to construct another word embedding. What I mean? We have attention scores, right? Those lines. And we have embeddings from another text. Then we will create some hidden representation of another text that pays attention from this token. So, how to do that? It's just it's this. We iterate over all possible word embeddings from y, multiply them by a attention score to receive hidden representation of a text. And as you remember, softmax gives us this. And the corner case is to put 1 on the most important word and zeros elsewhere. But we do this way. What's next? If you follow me using your laptops, you can choose any attention you like and put it into we created attention head. But first, let's code this. You see all these attentions, bilinear, minus, concats, and so on. Okay, bilinear attention is a layer. It receives embeddings with the size 64 and outputs embeddings with size 64. Here you can see x and y's, 3 tokens for x and 5 tokens for y. If we use this attention to, we call query something that pays attention to context, okay? If we'll pass y as a query, then output will be, the shape of the output will be the same as the shape of the query. This is why it did, because we aggregate all tokens from another text, okay? So, and another situation when we pass x as query. You can try LSTM, which I will not cover, and how we will use attention. As you remember, we have heads, simple heads and sneaky heads, but now we'd like to somehow use attention. Now head receives still 2 vectors, then 2 tensors. Then we, for each x and y, we pay attention to y and x to receive new representations of x and y. So now, think of it this way. Now, new x knows about y. It's seen what was here. And the same situation for y. It knows about x. So new vectors that interacted with each other, okay? what we can do next, we can concatenate or, for example, average with initial vectors. Here we concatenate. Here we average. Yes, here we average vectors. But also what can we do is we can just use, here we can concatenate, I'm sorry. We can use just one representations, new x and new y. And the rest is similar. Element-wise multiplication, difference, and so on. Yes? Why do we take mean? Because you see that x is a tensor. There are three dimensions in there, and ux and new y is the same, but the final layer, dense layer, needs vector, not a tensor, because let me put it this way. This is X, a matrix. Tokens, 1 token, 2 m tokens. We need to pass this thing into dense layer. Matrix multiplied by another matrix will give a matrix. But what we need to have is a scalar probability. So the simplest way how to transform matrix into vector is to average all columns. So using mean pooling operation. We also can do some CNN or max pooling or whatever. Here we choose mean pooling. Okay? So this is the final network. What can you see here? It has embedding layer, same as before. Then identity layer, which is actually just let me put it this way. Have you seen this guy? This is exactly identity layer. We just skip the body, but it's just a way to not to edit the code. We can just put, instead of body, we can put identity that just returns what you pass. Okay? And then we have bilinear attention, which uses embeddings, initial embeddings, to create new representations of texts. So we can train this network and see what it can offer. Perfect. Let's once again put our new score here. We'll call it bilinear head, okay? Bil head. And it's okay. Any comments on this? Any questions? Why or when or yes? Why increased? because we followed our intuition throughout the lecture to create new representations of text that know about interactions between two, we call it towers. One tower with one text, one tower with another text. We started with just multiplying vectors. Now we make the model know about another text to create a representation that knows about another text. So that's probably it. It just because intuition helped us to create something more efficient. Okay. But also, what can we do? We can replace identity layer with some LSTM and still train. I remind you that we have around 20K samples in our data set, in train set, okay? What limitations we have when we have such a small data set? Who knows? Limitations regarding engineering new architectures, new models. Yes, exactly. It should be shallow. That's why I firstly show you what if we remove body, just embedding layer in and attention head. Pretty simple. Few parameters in the network. But when we add LSTM, what we can see, it's overfits. But still gets close result. But you should think about this when you create new networks, because you don't have much data. That's why we don't like to have models with many parameters. So we call it Bill head plus LSTM, okay? It's something similar, but in the first case, the overfit was not as severe as in this time. Okay, let's try to visualize our learning. I cannot guarantee that everything will work, but anyway, we'll try. We'll run TensorBoard and see learning curves. For some reason, I cannot see runs, but I'm pretty sure different runs. Anyway, just as in our table, we see that attention model is the best, but we cannot see every model right here. Yes?
Could we use our fast text representation from Facebook instead of embedding layer?
Yes, of course we can. We can whether initialize our embedding matrix with fast text embeddings, or we can initialize and freeze this embedding layer. So two options. you and another option, you can initialize with fast text embeddings, and then fast texts, let's put it this way. And only for this layer you can set learning rate to be very low. So you won't forget the information you learned from the large corpora, okay? I don't know, something like that. Yes, we can. Any questions? All right. Let's see what we got. Just as in the example with the animal, we can see how our model sees information. Just a simple function that outputs this vector with attention scores. Here we can see X that pays attention to Y. All right. Why do queries download question they cannot answer? Blah, blah, blah. Why do queries answer question they already answered? As I said before, the intuition may work or may not work, because we'd like very much to see the animal example, but it's not guaranteed. But anyway, we can look at what's going on. As you see, label equals to 0, which means that this example's not attention. Let's find something that has the same meaning. How can I earn money online? How could I make money online? Okay, we see that I and online have the high score, okay? And therefore, actually, we can normalize, and we can skip normalization part. Anyway, and online, I don't know why, but online with online also have a high attention score. We can check for other examples as well. For example, okay. I'll try to find example with label equal to 1. That's strange. Wow. What we see, probably in these sentences, the word password is the most important. Probably, we don't know. And we see that words from this text pay high attention values to word password. So this is just a tool that can visualize your results, okay? But, however, this is all good, but it's a not real task. Let me explain you why. We were able to develop a model that can predict whether two sentences are paraphrased or not. All right? So we call it probability that, let's say if you see this sign, this means two texts are paraphrased. And we have many models that can do this, okay? But in reality, this model is useless. Can you help me understand why? What can you do with this model in reality? Paraphrase. or okay, let me put it like this: x, y. Labels, all right? If labels are equal, if labels are the same, and we have this model, can you imagine? Okay, as I said, this is a Quora question pairs dataset. Do you know what Quora is? Website where you can ask questions, right? How can they use this model in production? Okay, let's imagine I asked X. What do you do next? I came to Quora, asked X, then these guys from Quora try to find similar questions. How do they do that? Yes, Quora guys probably will use this model to retrieve paraphrases, right? So for example, person wouldn't ask this question because it's no good to have 1 million questions about the same. But anyway, I came with X. What will you do using this model? Exactly. Compare with each Y. This is Y. 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 How many Ys do you think Quora has? Okay. Let's write it this way. Everyone agree, right? That the shape of Y is more than 1 million. And any problems with that? Yes, search by tree, but we have a model.
We should recalculate the vectors for each question in our database, and since person creates question X, we need just to inference this one vector.
Sounds good, doesn't work because we have attention model. We cannot pre-calculate Ys. On the first step, we already calculate interactions between vectors. But this is a great idea, and this is what we need to do. Yes. So to summarize, if we have large Y, then we need, for each new question, we need to calculate. We need to inference our model exactly this number of times. Do you know how many times in a second you can inference this model? Any guesses? 100? Yes. Maybe 500. But this will take days. You agree? So that's why we need to come up with something. How to do that? First, I modified initial Quora dataset in the following way. I grouped all paraphrases together. So, for example, now there are almost 2,000 classes. Each class represents one paraphrase group. Let's look at class, for example, number 93. All these questions have the same meaning. How can I increase my presence of mind? How do I improve presence of mind? And so on, right? So, many labels, many classes, and not big data set. Any limitations, once again? What will stop us from developing something? The same idea about parameters in the network. Let me think of another task for this guy. At some companies that have voice assistants like Siri, Alexa, and so on, blah blah blah, Alice, right? They have predefined questions with predefined answers, right? Because like to answer for the question, what's your favorite movie? Exactly on the same, each time person asks. So these guys probably also have large number of predefined questions. Probably thousands, yes, but thousands is still a large number. And another problem is you need to understand whether new question is about predefined questions is or not, because as you remember, we can ask question using the same words, but this question will have another meaning. So the problem here is that if you'd like to train some model here, you'll need not only predefined questions, but you also need something that will have class -1. We call it not from any class above, all right? Because we need to, we don't like to answer to these questions. So one way to solve this problem is to use paraphrase retrieval as well. If you have, let's say, these predefined questions with the same answer, and in reality, you won't have many examples how to ask a question. Okay. So that's why probably it's a good idea to use paraphrase retrieval as a solution to this problem. Many classes, small number of examples in each class, and a large class that you don't like to answer. Okay, same as before. We split data set into train, dev, test, save it. And now batch consists of two objects, text and labels. Text is same as before, indices. We can padding tokens, right, and some indices. And of course, we can again look what each index mean. If something, something, blah, blah, blah. Very simple. We change model handler. Now it receives only X, one text, and outputs a vector that shape of which is number of classes, right? Shape 0, num classes. And then cross entropy and so on. Same as before, we use embedding layer. Embedding layer, averaging network, and the head, which from this small number of elements, you understand the problem here. Probably it's not good, because it's a large increase in number of dimensions in the last layer. And what it means is that you want your model to understand what text is about only by looking to two elements. This is not a good idea. Same as before, we start training process, and here F1 score is macro F1 score over all possible labels. Okay, still it can achieve good results, but this model overfits. Also overfits like the model before. You see that on the test set we have this small value, because the model is not able to generalize and to predict good outputs. How? The question remains, how to use this model to solve paraphrase retrieval task? Okay, triplet loss where? Yes, but naive approach would be to just calculate all pairwise scores. We can try to do that by running this loop. What it does, it iterates over all test batches from test iterator. It iterates over all train batches in train iterator, and it receives logits for each pair. You see, it's even for 20K examples, it's already an hour, even on GPU, right? So we're probably gonna stop this guy. and try to use pre-trained model to solve this problem. What we're going to do is, you're right, this model also outputs hidden representations of texts. This model not only outputs probability, but also outputs some hidden representations, right? And we still can come back to the idea of calculating the distance between hidden representations to, to approximate the result. So the idea is the following. Firstly, we will pre-store all access. We call them all possible texts from our train set. Then, when the new X comes, some question, we again using this model, receive X, hidden X, and we can run KNN, K nearest neighbor, that will output K samples from here. And then only among those two xk, only we will compare this new question only with K examples. This is a large improvement in terms of speed. And actually, you can tune K for your own system. If you have a supercomputer, for example, then it can be thousands. If not, it can be, for example, 10. I don't know. It depends on your computational powers. So the idea again is simple. Let me show what I mean. Text 1, text 2. We will pass these guys through model 1, which is embedder plus body. We will receive x1, x2, two vectors. Then we will store all x's somewhere, x. When we talk about KNN classifier, it's always about calculating distances between vectors, whether it's Euclidean distance or cosine similarity or something else. So we store all vectors from train into x train. Then, to speed up our head, which is the most computationally intensive part, because it calculates interactions. So head, what it does, it looks attention here, attention there in the head. Let's say it's attention. And it means that we cannot restore something in here because it's always a new result if you pass two different vectors. All right, so this is the idea. We use KNN to select K examples and only then pass those K examples to head in order to receive K scores. Okay. So in order to use fast implementation of KNN, we will use Face, just library from Facebook. What it does, it allows you to find the most similar vectors in a second, in a milliseconds. Okay. What can we see here? This code calculates all access from train iterator. Also, it calculates all examples from test iterator, stores them. Then we can select any k we like and try to do as I said. You see this Face index. We can search among X train by just passing one or many examples in there. I remind you, this is not very honest because this is a different model which was trained on another data set and something is not working. Here we use another model that trains on another data set, on another part of the data set. But still we can look at scores it can achieve. But again, I don't know why, but it should be a lot faster. Okay, let's continue the lecture without running the code for now, because it's actually we'll need few more minutes to end this lecture, maybe 10 or 15 minutes. I just need to explain the concepts. Okay, what I'd like to write down for now is the same table, but for the text classification task, where number of classes is large, but the number of examples is in each class is low. As we've seen before, it's not a good idea to use softmax, because you'll need many parameters in the last dense layer. So, classification. Same as before, algorithm, and F1 score. We tried running softmax, and we received 47. Yes. Now, what we're doing now and what's not working is pre-calculated, pre-trained model on another data set. Actually, on another part of the data set. Oh, here it goes. Pre-trained on other data. Some attention model that, as you've seen on the graph I showed you, calculates k-nearest neighbors and passes them through the network. As I remember, it will be something like, because this model was not able to generalize well, because 20K samples, not a large amount of data, and the model is not complex, just some simple model that, and most importantly, K equal to 20. We'd like to we'd like the KNN to approximate our results. If there is a right answer among these 20 samples, it's okay. But in reality, 20 examples is not good enough. So let's see what we got. Okay, let's wait for some seconds. We mentioned triplet loss, which is a good idea, which will not be covered today, but I'd like to show you the intuition. Same as before, model 1, which is embedder plus body. It takes some, let's say, I, J, and K for each of these stacks. It outputs embeddings. And then we can actually make our model to represent our vectors in the following way. We'd like to have texts that have the same label closer together in n-dimensional space, and vectors that have different labels as far away as possible in n-dimensional space. It can be achieved using triplet loss. So if from our batch, we find some samples with yi equal to yj and yi not equal to yk, then we say this is a triplet. We pass this guy to some loss function that calculates distances between xy, xj, then calculates distances between xy and xk, and we'd like this guy to, the distance between negative pairs be higher than distance to the positive pair. This is achieved by this. This is a max between 0 and this guy. And same as before, we can use multiple loss, not only to help the KNN to do his job. Same as before, these guys are passed into head. So this goes to triplet loss. And this goes to binary log loss. And then we can sum up them and backpropagate using two losses. This actually works, but it's not implemented here. You can try it at home or anywhere else. Even lower than I expected, but because as I remember, I checked it on k equal to 100. But okay, If k equal to 10 or 20, then it's this value. But now, from our initial data set, which is this, text and labels, each label represents one class, and 1717 is -1 class. What I did, I collected another data set from this. As you understand, you can transform this data set into a Paraphrase data set by sampling 2 examples from the same class and sampling 1 example from another class. So this is commented code. It works like 10 minutes, but we don't have that much time. And it's a naive approach. It's what you should do in reality. You should collect Paraphrase dataset online, not offline. But here we calculate Jacquard similarity between 2 texts, and if this Jacquard similarity is higher than 0 and lower than something big, and these 2 texts T and Tn are from different labels, then we say it has 0 class. If also we sample text from the same class, and text from the same class, absolutely, I'm absolutely sure they have the same meaning, right? So instead, we can just load pre-calculated dataset. What can you see here? What is the best question on query ever? What was the best query question ever? What else? Also, there are some 0 classes. So yeah, from this dataset we did this. Now it's of shape 15K. I don't remember the class imbalance, so let's check. That's strange. Okay, anyway, very computationally intensive operation. Let's wait. And what we'd like to do, we like to use this new data set to again train attention model that can say whether 2 texts are paraphrases or not, and then use this model in our KNN pipeline. All right. Balanced data set. That's great. Again, we save our data, create attention model, same as before, embedding layer, and so on. And yes, just something's wrong with the server. Okay, actually, what's left is I need to press 3 buttons and receive this score. As you can see, k still equals to 20, and trained on the same data. Why it's cool? Because when you have larger number of classes, for example, if you're from Quora, or if you have even larger size of your data set and of the number of -1 classes, then this is definitely will be your choice to use attention to solve text classification task. Attention models as Paraphrase identification model to solve text classification. Text classification. In conclusion, when this will work, usually, I'm repeating myself, but anyway, if you have small number of samples in each class, if you have many labels, this is very specific problems, but anyway, there are sometimes in production, in reality, this is exactly the thing about real life. And optional, if you for some reason you don't want your model to predict something, this is -1 class. At Tinkoff, think of this way. Sometimes bot doesn't know, and bot is not confident whether he should answer or not, because lower scores and so on and so on. Probably it's better to just pass this question from the client to the agent, to the real human that will answer properly. Okay? What? So that's it. We use it at Tinkoff for predefined questions, and it works good compared to text classification and other approaches. So thank you for your attention. You can ask me any questions you like. Also, there is a Telegram link. If you, for some reason, not asking me now, you can contact me here, or you can, I don't know, write me an email. But so, thank you. Your question. Yes. Mm-hmm. Yes, but it doesn't solve the problem, because you said that the model doesn't generalize, right? But heuristics don't generalize at all. Could you give me an example of smart hand-based approach?
Not hand-based, some approaches which are rooted in the computational linguistics, not machine learning. They are based on the, I don't know, on morphological analysis, semantic analysis, and so on.
Okay, of course you can combine any model you like with another model to have a model that's based on heuristics, model that based on some morphological analysis, machine learning models, and so on. So the question is what you're trying to optimize. What?
Yeah, actually, I'm a specialist in computational linguistics, so I just wanted to hear your opinion about this, because there is some tension between people who love machine learning and people who love linguistics.
I can imagine cases when some linguistic tools would be more powerful than deep learning. Yes, of course. Other questions? Okay, thank you. Oh, okay.
What values of F measure are suitable for production in Tinkoff?
At Tinkoff, we don't look at F1. What we are trying to maximize is the following metric. As you know, we don't have any in-place buildings where you can come and ask a question. That's why all communications with clients are held whether in chat or via the phone. Okay. Bot cannot answer wrong because it will lead to the financial losses because clients will go to other places, other banks. That's why we say precision should be above, I don't know, this value. This is one part of the metric. And then we say we'd like to maximize recall because we'd like to have fewer number of agents, human beings that answer in call centers because it's very expensive to have large call centers. So this is actually what's optimized, not F1.
Do you take into account that different questions may incur different financial losses? For example, you may lose very rich because of this report, you might just...
Yes. Yes, if the question is, of course, you can calculate precision and recall for each label, for each class, and then if some class is more important than another, you can increase this guy here. Yeah, that's true. Okay, thank you very much.